We're going to finish up Chapter 5 with Section 3. Section 3 is on the binomial distribution. So, get a little backwards, get a little ground gang into what this is about. A lot of times when we're using statistics, we repeat the same experiment many times to see what happens. Each repetition is called a trial. And we're going to focus with this lesson on experiments that only have two possible outcomes. So examples of this would be, how effective is a drug? Each patient would be a separate trial. It's either effective or non-effective. Sales, weekly sales of a salesman. Each customer would be a trial. Make the sale or they don't. Well, these are type of things we use statistics to do, and it's a yes or no, two possible outcomes. This is where binary comes into. Why did it do that? Okay, because I'm in the wrong spot. So, with that in mind, we're looking at, with this section, analyzing repeated trials. To do this, we're going to kind of work up to it. Is first we need to calculate factorials. Then we're going to use factorials to find something called a binary coefficient. And that's going to get us into what we call a Bernoulli trial. And with these Bernoulli trials, we can finally make our binomial distribution. So, wow. Bunch of vocabulary, bunch of new things building to what we finally need to get to. So we'll start with factorials. You might have seen these before or not, but factorials, we represent it with that exclamation mark. And it's really, we're just multiplying all of the positive integers up to our number. So, I know this looks weird. So k factorial is going to be k times k minus 1 times k minus 2, blah, 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 all the way to times 1. So, if I wanted to do, say, 10 factorial, this would be 10 times 9 times 8 times 7, and we go all the way down to times 2 times 1. We're just multiplying all the numbers between 1 and 10. All of the integers. Now, to make this work, we define 0 factorial as 1. So, because 0 times all the numbers between 0 and 1 just doesn't make sense. So, we use that definition as we're going through that. So, give that a try with these problems. Pause the video if you need to, but find these 4 values. So 4 factorial, 4 times 3 times 2 times 1, 24. 5 factorial is 5 times 4 times 3 times 2 times 1. Yeah, it's kind of 6 times 5 times 4 times 3 times 2 times 1. Couple things I want to show you with this. First thing is, on your calculator, look for the factorial button. If you have, let's clear that off. I know most of my students have the TI. If you hit the math button, and then you arrow over to probability, you will get an option that will give you that factorial. And pretty much all of your scientific calculators, you will be, if you look closely, you'll find a factorial button on there to help you do that. It might be under a probability menu, it might not be. So that will help you. One thing that helps you out through some of this. But the other thing, notice, when we took 6 factorial, it's just 6 times 5 factorial. Or 4 times 3 times 2 times 1 is 6 times 5 times 4 factorial. So sometimes when you know one factorial, it can help you find the other ones. We kind of make use of that in some of our formulas. So that gets us to something we call a binomial coefficient. And another term you might also remember binomial coefficients if when you're looking at deeper into probability and looking at different counting theorems, we use combinations. We say n choose x. That's another way of writing this binomial coefficient of n over x. And this is also under your math prob menu on your calculator. So you're going to need, I want you to be able to use this formula and factorials. I also want you to be able to do it with your calculator and bring that up. And there's, when you get on spreadsheets, when we look at the labs, we'll look at ways to do this binomial coefficient using a built-in function on your spreadsheet. So there's lots of ways to find that, but we right now need to define what we mean when we talk about the binomial coefficient. So with this, we need to say x is an integer, non-negative integer, but it has to be less than or equal to n. So this idea of n choose x is the way we often will say this, is I have n items and I want x of those items. And that gives me my combinations here. We can calculate by taking that as n factorial over x factorial divided by n minus x factorial. They're called binomial coefficients because if you do the binomial expansion, binomial is 2, so we have two terms, a plus b to the nth power. We can use this to find the coefficients of that expansion. So if you get into pre-calculus, calculus, that's something you might need to use. There's also some cool things with binomial coefficients. If you want to look up Pascal's triangle, I'm not going to go into that in this discussion here, but it's something worth, if you have a little time, Google it. Might see a little bit more of Pascal's triangle. It's another easy way to find these binomial coefficients sometimes. So, give this a try. And I would like you to try this. Use the formula to do these. And then double check it with your calculator. So pause the video, try to find these, then start it back up, and we'll work through showing using the formula to do these. Five choose 1 is 5 factorial, 1 factorial of 5 minus 1 factorial. So that should give you 5. We go 6 and 4. 6 factorial over 4 factorial times 6 minus 4 factorial. You notice right here, this is where we're taking advantage of the 6 factorial with 6 times 5 times 4 factorial, so I can cancel out the 4 factorials. So we don't always have to calculate all those numbers. That kind of helps when we're doing this by hand. So just work through those other ones. Here's why we need to define a 0 factorial, because in this formula, I get 0 factorial, don't I? So in order to do these binomial distributions, you're going to have to be comfortable doing these binomial coefficients. So whether you use this formula with the factorials, whether you have figure out a way to make you do on your calculator, you need to know how to do this. So let's get to Bernoulli Trials, and they're called Bernoulli Trials because of the guy who started doing this was named Bernoulli. Mathematicians, it's either name it by what it does or name it by over yourself, right? So a Bernoulli trial is a very specific type of situation. We're doing repeated trials of an experiment, but we need the following conditions. We have to be a binary type of, it's either success or failure. There's only two outcomes. We'll generally use that S and F. The trials have to be independent. So think like flipping a coin, doesn't matter how many times you flip a head, you still have a 50% chance of getting heads on the next flip. They're independent. What happened before has no effect on what's going to happen in the future. And finally, the probability of success, that P has to remain the same from trial to trial. So when we're talking about, say, drawing cards out of a card from a deck of cards. If you draw one card, you do it with replacement, draw one, stick it back, that's independent. Your probability is going to remain the same. But if you say, okay, I'm going to deal out a set of 5 cards, now the probability on each card is going to change because there's fewer cards in the deck. So we can't have that going on. For a Bernoulli trial, the probability of success has to be the same from trial to trial. So the binomial distribution, which is what this whole thing is about, is basically the probability distribution for a number of successes in a set of Bernoulli trials. So that's all this has been dealing up to, kind of wind up to get to what we need to do. So we're going to do another, I just love the examples in this textbook. So mortality rates. But basically, they use those when they're trying to figure out, how long a person is going to live. What should life insurance premiums be? What should pensions, annuity payments, type of things like this? So we're going with this information. The National Center for Health Statistics has said a person who is 20 years old has about an 80% chance of being alive at the age of 65. So we're going to look at 3 people picked at random. Whoops, no. Okay, so we look. Each trial consists whether the person who's currently 20 will be alive at 65. So that's your 2 possible outcomes. At age 65, they're either alive or dead. So we're going to say success is they're alive. Probability of being alive is 80% or 0.8. They're independent because what we pick from the first person should have no effect on the second person or the third person. So we look at what are the possible outcomes, and we get those 8 possible outcomes here. All 3 are alive, 2 alive, 1 dead, alive, dead, alive. So those are my 8 different possibilities for what's going to happen to these 3 people. So we can, for each one of these, figure out, because each of these are independent, so we can use our special multiplication rule to say the probability of all 3 being alive is 0.8 times 0.8 times 0.8, and so on and so forth. So we can figure out the probabilities for each one of these. Now sometimes we do this with a tree diagram, and we've used tree diagrams in the past in middle school, especially grade school, middle school, when we're doing prime factorization. But we can, again, look at this. At any point, we pick the first person. They either have success or failure. So 80%, 20%, we're going to mark those. Then we pick the second person, either success or failure. If we pick the failure first, then the second person, success or failure. And so we break off this tree, but on each branch we're going to put the probability. So then to find the probability of my 8 outcomes, I can just follow the branches. 0.8, 0.8, 0.8, 0.8, 0.8, 0.2, 0.8, 0.2, 0.8, and so on and so forth. So I can calculate what is the probability for each of my 8 possible outcomes from this Bernoulli trial. So if X is going to be the number of people alive at age 65, using that tree diagram, we can now find our probability distribution. So, yeah, I hate Queef's doing that. Let's go back. Come on, come on. Okay. So the 0 and the 3 we already did. To figure out, say, one person alive, we can come back here and say, okay, one alive, one success. We got a 1 here, 0.32. 0.32 and 0.32. And again, these have no overlap. They're mutually independent. So I can just add those 3 probabilities together to get my probability of 0.96. And the same way I find my probability of 0.384 for 2 alive. Okay. Okay, jumping ahead. So here is my probability distribution. Here's my histogram now. We can kind of see what that's going to look like. So here's where the binomial coefficients come in. So with just 3 trials, we could make out and list all the different possibilities, all those 8 possibilities of what could happen. If we're starting to get more and more, if you're trying to draw that tree bigger than 3 choices there, it very quickly becomes unwieldy, and you don't want to do that. But the number of successes, where we find out, is going to actually equal the binomial coefficient. So if we say we have 3 trials, 2 successes, we can do that 3 choose 2, and that would give me how many trials, how many of those options will give you that situation, and I can use that to figure out. So, for example, here I got 3 trials, 2 successes. That means that happened 3 times. So I can just say, well, the probability of 2 alive, 1 dead are going to be 0.8, 0.8 times 0.2. And as soon as my thing goes away, I'm going to get my 3 choose 2 times 0.8 squared times 0.2. And that gives me my 0.384. And this is where those binomial coefficients come into play. We can use those to figure out how many of my outcomes would fit that pattern of success, that number of successes, that random variable. That gives me the binomial probability formula, and this is what we really need to get out of this. X is the total number of successes in n trials with a success probability of p. So we can find that probability that x equals x is going to be number of trials. This is number of successes. Probability of success raised to the number of successes. 1 minus p, that's the probability of failure. N minus x is the number of failures. I have x successes, n minus x failures. So that's basically what that's doing. X is my binomial random variable. The binomial distribution has, we say, parameters of n and p. So parameters, we're talking about a population. The 2 things that affect this, the only things that will affect this distribution, are how many trials we did and what's the probability of success. It doesn't matter what the trial is, what you're doing. All of these, if they can be described as a series of Bernoulli trials, the distribution is going to depend wholly on how many times did you try it and what's your probability of success? Because that's the only variables plugging into this formula. So, when we do this, again, here's your kind of a step-by-step guideline. We need n trials. We need it to be, it has to be a Bernoulli test. So there can only be two outcomes, success or failure. The trials have to be independent. And the success probability has to remain the same from trial to trial. That kind of has to do with independence in there. So you just identify what do we mean by a success. You need the probability that you have a success. You need the number of trials. And then you can use this formula to find the probability for any number of successes. And you put them all together, you get your binomial distribution. So, here's the problem. Kevin's a great pizza fan. 70% chance he'll have pizza for dinner on any given evening. We're going to pick 5 evenings at random, and I want you to find these probabilities. He has exactly 2 times. He has it at least 3 times, at most once, and then make a probability distribution. So pause this video, give this a try, see if you can do this yourself. When you get to the point where you have it, or you're just frustrated and you're not getting anywhere, start this up and I will walk you through this. So first, identify a success. Success we're going to call, he has pizza for dinner. Success probability is 70%, so P equals 0.7. Number of trials. We have 5 evenings, so N is going to equal 5. Remember, I need N and P. Those are my parameters. With those, I have my formula. I can determine any of these probabilities. So my formula now is going to be this binomial coefficient, 5 choose x, 0.7 to the x power, 0.3 to the 5 minus x power. So I can use this now to answer those questions. Exactly 2 times, we plug in 2 for x. We get a 13.23% chance that Kevin had pizza exactly 2 times. Had pizza at least 3 times. We have to look at least 3, so 3 or 4 or 5. So those are all independent. We can use special addition rules, so we find each of those separately. By using my same formula, I'm just plugging in a different value for x. I get those 3 probabilities. I add them all together, and the probability is 0.837. Or 83.7%, he will have pizza at least 3 times out of those 5 you picked. At most once. So that could be 0 or 1. So again, here's for 0, here's for 1. Add them together, and we have 3% about that he had pizza at most once on those 5 days that we picked at random. So for the probability of distribution, we're done, because with those questions we have found, because first we found 2, first we found 2, then we found at least 3, so 3, 4, and 5, then we found at most 4, which was 0 and 1. We find those all together, they add up to 1, about, rounding errors in there, so that looks reasonable. So sometimes we deal with something called a cumulative probability, and that's going to become even more important when we get into the next chapter. So cumulative probability is when we're going less than or equal to a specific number. So we say basically we're saying at most 1, that's a cumulative probability. We want to say at most 4 times. We'd say 0 plus 1 plus 2 plus 3 plus 4 and add all those probabilities together. So that's what we mean when we talk about a cumulative probability. So, and this is done enough that we have tables for that. So if you're one of my students with our textbook, it's in Table 11 and Appendix A is a binomial distributions that will give you the cumulative probabilities for it gives you all of these based on your parameters of n and p. Because again, n and p are all that matters. How many trials are there? What's the probability of success? Every time you have the same n and p, you're going to have the same distribution. So we can make up these tables and just look it up and not do all these calculations. Kind of nice, huh? So, again, when we look at the shape, if the probability of success is 50%, you will have a symmetrical distribution. If it's less than 5, it's going to be right skewed. If it's greater than 0.5, it's going to be left skewed. So those are some basic ideas. You can look at it and determine what shape you're going to be in. So I want to finish up here with expected value. The expected number of times Kevin would have pizza out of 5 evenings picked at random. So pause this video and try to do this. Use this, what we did last section. Let's clear this off. Find me the mean and the standard deviation using those formulas we did in section 2. So pause this video, calculate these out, see what you get, and then come back. So to find mu, we're going to need x times the probability of x equals x. So we multiply those out, we get 0, 0.0284, 0.2646, 0.9261, 1.4408, 0.8405. We add those up together, we're going to get 3.5004. So my expected value is 3.5, approximately. To go ahead and find sigma sub x, I'm going to use the computing formula, which was the sum of x squared probability x equals x minus mu squared, because it sounds like it's easier to do. So if I'm going to go x squared, 0, 1, 4, 9, 16, 25, I go x squared probability of x equals x. I'm going to get 0.0284, 0.5292, 2.7783, 5.7632, 4.2025, giving me a total of 13.3016. And if we subtract this from this, we take our 3.5 squared and take the square root of that, we're going to get my sigma to be 1.02. So that's using this what we did in section 2. So hopefully you're feeling better with that. Just a quick little double check on it. Now let's find the easy way to do this. The mean and standard deviation of a binomial random variable with parameters n and p. I'm just going to give you these formulas. Mu is n times p, and sigma is the square root of n times p times 1 minus p. So number of trials times success, probability of success times probability of failure. So if you do that with Kevin's dinner with n and 0.7, we get 5 times 0.7 is 3.5. 5 times 0.7 times 0.3 is square root that, 1.02. That's just what we did doing all that hard work. Binomial distributions are much nicer. On average, out of 5 evenings, Kevin will have had pizza 3.5 times. The number of times he has pizzas will differ from this mean by about 1.02. That's that standard deviation. Last thing I want to say is hypergeometric distributions. These are all based on Bernoulli Trials. We do random sampling with replacement. What if we're not doing it with replacement? If we have then the success probability is going to vary from trial to trial. So this is now called a hypergeometric distribution. It has its own formula. Here's the good news. I'm not going to give it to you. The trick is, if it's a small enough sample, if the sample is less than 5% of the population, the difference in the success probability is so small we can approximate this with a binomial distribution. So as long as we can keep that sample a small enough percentage of the population, we can go with and assume Bernoulli trials and use these formulas we have. So give that a try. Here are some problems to do out of your book. Enjoy.